Hey folks, welcome back to the channel. My name is Thomas Rintoul and this is the last video in my series on my master's project. I've been bringing you guys along talking about what I've been up to, the sorts of challenges that I've faced, what is involved in doing an astrophysics master's project. Last time we looked at some of the core results of the project, and in this video we're going to be talking about some extra little results that we found, as well as how I've been assessed, and then we'll round it all out with a Q&A from questions you guys asked on the last video. So let's talk about episodic accretion. I'm not expecting you to know what that is. Let me explain. So accretion, for those who are joining us in the series at this point, is the process that lets mass get onto a star or any other body, like planets can accrete as well. But in this case, we're looking at mass accretion onto stars, specifically triple systems called hierarchical triples. So that's accretion. What is episodic? Episodic means that we have variations in the accretion rate where we see a rise and then a fall, and this can happen either periodically or just randomly, and then it stops for a while and then it does it again later. There are different types, and this is the graph showing mine. What we have here is a periodic episodic accretion. Now, if you're in astronomy, you might be wondering why I'm talking about episodic accretion as if it's this new thing that we found. Haven't we found it before? And yes, episodic accretion has been seen before. Typically in systems we refer to as fluors and XRs. These are systems where we've seen episodic accretion for single stellar systems. And quite frankly, this is completely different in what it shows and what it looks like. The reason for that is that fluors and XR systems see insane levels of accretion bursts. They see a factor of 1,000 difference between a non-episodic rate and an episodic burst of accretion. Factor of 1,000. By comparison, my episodic accretion in my simulations is only around a factor of 2. The other big difference is in timescales. Typically, fluors and XRs will only see episodic bursts lasting at most about 15 months. My episodic accretion is periodic on a period of around 36 years, twice the wide binary orbit of my hierarchical triple systems, actually. The other fundamental difference between my episodic accretion and a fluors or XR system is that this is consistently periodic and it keeps happening. It's tied to the orbital properties of the multiple system, not to some other factor as you would have for a single star doing episodic accretion. So there are a couple of questions that we have to ask. Firstly, is it real? Like, is this something in the simulations that is actually there and should be there? And then if it is real, what's causing it? So to cover, is it real? I think it is, based on the fact that I thought it was a bug initially, and I did everything in the simulation to try and get rid of it, including running it at an insane number of resolutions from like 10,000 SPH particles, 10,000 particles in the simulation representing the gas, all the way up to 5 million, and you still see it across the entire range. So I think yes, it is real, and I've changed a lot of parameters and it still doesn't go away. So I'm convinced that within the simulation parameters we've given it, it's real. I'll come on to a caveat on that in a second. If it is real, what's causing it? This is where I bring in the caveat. My simulations are running at a rather unphysically high viscosity. Now, viscosity is it's a measure of how sticky the fluid is, how much it sticks to itself. So for example, water has quite a low viscosity, whereas custard or syrup has a really high viscosity. My fluid has an unphysically high viscosity for a typical disk around some forming stars. The reason for this is that accretion is governed by viscosity. A higher viscosity means you get higher rates of accretion. Now, the reason that I think this may be the problem is that in having a very high viscosity, I think too much gas may be getting funneled into that central region where the stars are, and that the stars can't accrete all fast enough. So this episodic accretion is perhaps a self-regulating mechanism. This is something I would need to do further work on. Please do not take this as gospel. It may be completely wrong, but that's my guess on it. But episodic accretion and the trends that we talked about in the last video are not the only thing that I found. I also found cases where my episodic accretion just stops. Not that the accretion stops, it stops being episodic. The accretion rate increases and becomes continuous. It increases to a maximum and then decreases slowly. This is interesting. This is what we discovered to be resonant accretion. If we look at our density with radius over time, you see these massive excitations in density, which frankly is really cool, but hard to explain. And it's, yeah, basically, this is kind of new, and we don't have a good understanding of what the mechanism is yet, and I didn't have one when I put in the thesis, so I don't have a better answer for you either. This is a really interesting thing that I would like to be able to study more on. Unfortunately, I didn't have time in the project, so I guess either I'll have to do it at some other point in time in the future, or somebody else will have to do it. But let's move on from all the results I can't fully explain, and talk a little bit more about the project as the final assessment of my degree. The main way that a project is assessed is through writing a thesis, a 20-page document in this case, that just basically says, what have you done? What are the results? Why is it interesting? And it shows essentially that you've done all the work and that you understand it. Ultimately, for a master's project, it's similar to writing a scientific paper. It's just a long scientific paper. So inside your master's thesis, there is everything from an introduction that sort of sets the stage for your whole field. Where does your research fit in with it? You then talk through, in my case, the sort of methodology, the simulations that I was running, the initial conditions that I ran at, and why. Then you go through all the results, you discuss your results within the context of the literature and what it could mean physically in the case of a simulations project, and then you draw up some conclusions and you hand it in. That's essentially what my project report looked like, and it was actually quite fun to write. I really enjoyed doing the write-up. It's quite fulfilling to be able to summarize all of your thoughts within one document and then hand it in for somebody to read it and for somebody else to actually fully appreciate what it is that you've been doing for like 3 months. I also spent quite a bit of time making it look pretty, making my plots look nice, and having all the formatting look great in LaTeX. The project report is not everything. There is also a viva. Now, a viva is an oral examination where, in this case, they will vary from place to place, but in the case of a master's project at St Andrews in physics, you give a sort of 15-minute presentation on your research, on your project, and then there's another 10 to 15 minutes for academics in the school, professional astronomers, to ask you questions about your project. And I'll be honest, it was a little terrifying going in, but once I got into the swing of it, it was fine. There were occasionally questions that I was like, I don't really know the answer to this. There were some that I was able to sort of hazard a guess at. Maybe not hazard a guess at, but logically reason my way through an answer. But there were others that I just had to say, I'm gonna be honest, this was not within the scope of the project, and I don't know. Ultimately though, that was the final bit of assessment for the project. And it was the final bit of assessment for my entire degree. It felt very odd walking out of that lecture theatre where I gave the talk and then walking out of the physics building and just thinking, right, I'm done. But this video isn't done because we're going to get on to some of your questions. I asked people in the last video and in the community tab on YouTube to ask me some questions about my master's project, both from the science point of view, but also just from the point of view of doing a master's project. So I have a few questions from you guys and let's answer them. All right, so your questions. There are a few from both the project video last time and from the community post on YouTube. So, first question comes from Bendy Bruce. This is probably a stupid question. That's what he said, I'm not just saying that. But the fact that you're studying 3-star systems would seem to imply they are by definition chaotic, the whole 3-body problem thing. Wouldn't that make it significantly more difficult to draw consistent conclusions, or is that completely irrelevant to what you're actually researching? Very, very good question. Not a stupid question in the slightest. I should have made this clearer in previous videos. Yes, you are correct in saying that 3-body problems, 3-star systems, are inherently chaotic. However, I am studying what are called hierarchical triple systems, which are the only 3-body system that have any measurable amount of stability. The reason for that is that a triple system, in this case a hierarchical triple, has got a small binary and a single star. So you've either got a massive single star with a small binary orbiting it, or you have a small binary in the center orbited by a single star. And the separation between those objects is very large. So you've got your small binary in the middle with a separation in these simulations of around about 1.5 to 2 astronomical units. And then you've got this other star that's another 10 astronomical units away, 5 times the distance. And the reason that this can exist in a somewhat stable format is because you've got a relatively stable binary system in the middle, because binary systems are very stable. And then you've got this other star which acts to just perturb that system, but not to greatly perturb it. The problem with other triple systems that aren't this hierarchical is that you get 3 stars approximately the same distance from each other that start orbiting, and eventually two of them get too close to each other and you get a slingshot effect, and normally one, if not both of them, gets ejected from the system entirely. Because my systems are hierarchical, they can maintain stability a lot longer. I don't know exactly how long any of these systems would continue to be stable, but they're stable for at least 100 wide binary orbits for around 2,000 years. Essentially, yes, three-body systems, triple systems are chaotic, but these ones have a range of stability where, as long as your separation between your single star and your small binary is large enough compared to the separation of the small binary, you should be able to have a relatively stable system for a very long time. Hope that answers your question. The next question comes from the Johansson. I may have missed you touching on this, but apart from the publication that inspired this work also probably did this, what is the motivation behind the Gaussian smoothing? For those who didn't see the last video, Gaussian smoothing is a weighted average that is allowing us to smooth out any variations to be able to compare accretion rates between different stars. I've used it in the previous video to smooth out the episodic accretion to allow us to compare things better. Phrasing the question differently, what makes you think the spikes are a numerical artifact rather than a real phenomenon? Okay, so to answer this question, I think it's partially been answered by what I've talked about in this video already, but I maybe should have made it clearer in the last one. I don't think that the spikes that I was smoothing out, which are the episodic accretion I've been talking about in this video, I don't think they're a numerical artifact. The reason for the smoothing in the previous video was to allow me to compare different stars to each other. So to be able to look at the single star and compare it to the small binary, see which one is accreting more, and to be able to better compare different systems to each other. That was why I was using Gaussian smoothing, because if I didn't smooth out the episodic accretion to make those comparisons, you just had a load of lines that all overlapped with each other. So that's why I was using Gaussian smoothing for what I talked about in the last video. It wasn't because I thought it was a numerical artifact, it's just that smoothing out that real phenomenon allowed a better comparison, because I could see, okay, what is the average rate over an orbit over time, as opposed to, right, so at this time, it looks like that one's higher, but it's being overlapped by about 3 or 4 other lines, so it's hard to see. It was just to separate out the data. Moving on to the next question from Daniel Hertberg. After your undergrad, what made you know that you wanted to continue studying besides just curiosity? First, clarification. I've been saying I've been doing a master's project. That is correct. I haven't graduated with an undergraduate degree yet. I'm doing something called an integrated master's degree. This is a degree that is 4 years in England, Wales, and Northern Ireland, and it's 5 years in Scotland because we have an extra year at university. This means I don't graduate with a Bachelor's of Science degree, I graduate straight away with a Master's in Physics degree. But the question still stands, why did I choose to do the extra year and get the Master's degree rather than finishing with a Bachelor's degree? The reason that I did that is that I want to do a PhD, and I've wanted to do a PhD for a very long time. I really enjoy doing research. I'd done a research project during my 3rd and 4th years and really enjoyed it, so I was like, I want to go and do a PhD. The natural thing is to do a master's before that, because it's hard, especially in physics, to jump straight from BSc to PhD level. Having that master's degree in there makes it a lot easier. The other thing is that it doesn't really cost me anymore to do it, other than just living expenses, because I live in Scotland and I'm from Scotland and I'm going to a Scottish university. And in Scotland, we don't have tuition fees for your first degree. It would have been more expensive for me to do a bachelor's degree and then decide later on, oh, I want to do a master's degree because I want to do a PhD. If I'd had to go somewhere else to do the master's degree, I would have had to pay for it, whereas doing it all as one thing here meant it was free as well. Like the tuition was all free. There is a level of it's curiosity. I enjoy learning, and if I'd left with a BSc, I would know significantly less about astrophysics than I do now, and it would have rather closed the door on me doing a PhD, at least in the short term. I would probably have had to go and do a master's somewhere else. So that's why I did the master's and why this whole series exists. One more question, and then just a comment I found funny. A question from Lee Sneeze, which I think came from the post. Have you tried out Julia Lang? I'm assuming this is the Julia programming language, and this question has been inspired by the fact I'm using Python. To answer the question quickly, no, I haven't tried it. But as far as I understand, Julia is meant to be a language that lies sort of halfway between the likes of C++ and Fortran and Python, in that it can be almost as fast as a very low-level language like Fortran or C++, but that it's a lot easier to write these programs similar to how you use in Python, because there can be a lot of built-in functions and packages that you use. It's an interesting one. I haven't used it, and I'm not entirely sure that I will end up using it. Ultimately, there are languages within astronomy that are just so widely used that trying to bring in another one would make things difficult. So Python is really widely used in astronomy for data analysis. There are entire packages like AstroPy and SpecUtils, which is for like spectra stuff. There are a load of packages that have been developed for doing data analysis in astronomy. And then for simulation wide, we actually want the additional speed that you get from using something like Fortran or C++ versus Julia. Now, I know Julia is faster than Python, but I don't think it's as fast as C++ and Fortran. So for big simulations, we need the speed there. So we don't, in a lot of cases, we don't really have a reason to meet in the middle with Julia. Most people in astronomy, if they're doing simulations, will have learned Fortran or C++ or both for running their simulations, and then Python. And I don't think that there's that much appetite for one language that does both. I might be wrong on that, and maybe in 10 years' time, Julia will have made its way into astronomy. Well, maybe not astronomy. Maybe in 20 years it'll have made it into astronomy, but in other fields it will have started taking over from Python. But I think just the sheer popularity and the wealth of information on Python, and frankly the number of packages that exist that people don't want to redevelop, I think with that much stuff going on with Python, I don't think it will replace it. And I certainly don't think it's going to replace the likes of C++ and Fortran, these low-level languages which are needed for efficient, fast simulations. Because when we're dealing with simulations that take months, a 10% difference in speed is a lot. That's just answer the question on Julia. And then the final comment was holy moly, I wasn't aware that people still learned Fortran from Likebot. Yeah, Fortran is still used pretty extensively in astronomy. For those who don't know, Fortran is a very old programming language. It was one of the first ones. Like, if anyone's seen Hidden Figures, the movie about the African-American women at NASA back in the 60s in the space race, the computer they get, the IBM machine, they had to learn Fortran to program that computer to make it do what they needed it to do. It's a more evolved version of that programming language that I know. It's called Fortran 90. There is now, I think, a Fortran 2018, which I'm sure we will start being able to use in things, but essentially there's a lot of things that are still built on Fortran 90, so we're leaving it there for a while because everything works. We still learn Fortran because it's still used in astronomy. My master's project used a code called Phantom, and it used Fortran, and yeah, that's what it was built in. So yeah, that rounds out all the questions that I've been given on this master project. Thank you very much for watching this series, and I hope you've really enjoyed it. There'll be some videos coming out in the next wee while talking about what's next for me, and I really hope that you'll stick around for them. Please subscribe and hit the bell icon. If you're looking for something else to watch, then why don't you have a look at this video here. It's about galactic center star formation and the 2020 Nobel Prize. Thank you very much for watching. I will see you in the next one. Have a very good rest of your day. See ya.